Okay, so we're going to be doing contextual review, Unit 4. Today is April 20th. That's when I am recording this. So if you are paying attention, this is the date that we're going with. And just to make sure, you watch these at your leisure and go over the notes when you can. It's not mandatory that you do, but if you have a question on anything, let me know. This is just kind of a recap worksheet that you got on Google Classroom, and the recap worksheet is going to be a kind of overview of what has been going on in this class. And then there's a review activity, which I will do as well and post that up. And the next one of the other videos is going to be on L'Hopital's rule. So let's get started with this. This is interpreting the meaning of a derivative. And so in the definition, or in this instruction, it says the function c of x gives the cost of digging a hole that is x feet deep. So when you're digging a hole that is x feet deep, this is your independent variable. All right, x feet is your value that's inside. This is in feet. This is your cost. Okay, so the cost is the whole thing. The x value is how big the hole is, how deep. So C of 20 is equal to 140 means that a hole 20 feet deep costs $140 to dig. Now making sure that we understand units in this case, money is the cost usually, and x is in this case feet. Okay. So when I look at this and I see c prime of 20 is equal to 5, I know that c prime of 5 is a slope. This is your derivative, so that is your slope. That is a rate of change. So that is a rate of change of the cost in terms of x. So the rate of change of cost. So that means that when the hole is 20 feet deep, the cost of digging is blank at a rate of, here's my rate, there's my rate, 5. Now what is my rate? My cost, which is dollars per x is in feet. So it's $5 per feet, and because it is positive, the cost of digging is increasing. Okay. Cost of digging is increasing. 4.2, a particle moves back and forth along a horizontal track from 0 to from time equals 0 or greater than 0 to less than pi over 2 minutes. The particle's position, which is in feet, is given by the function s of t is equal to 1/2 tangent of t. Find the acceleration of the particle at time t is equal to pi over 6 minutes and indicate the units of measure. So if we're looking for, in this case, we're given this function, which is our position. We're looking for the acceleration at that specific time. So when we're looking for the acceleration at that specific time, if this is my position to go to acceleration, I need the second derivative, which is the first derivative of velocity, which is a of t. So I need the derivative of s of t. So s prime of t is going to equal the velocity of t. And so this 1/2 hangs out. I need the derivative of tangent t, which is, you should know, and one of those trigonometry derivatives you should know is tangent t has a derivative of secant squared t. And so now I need the derivative of the velocity, which is going to give me the acceleration. This 1/2 still hangs out. And now secant squared t is going to be a chain rule because it's secant t squared. So I'm going to treat it as secant t squared. So I'm going to bring out the 2. I'm going to keep the function and drop it by 1, which it means it goes to 1, power of 1. And then I'm going to multiply by the inside derivative. And the inside derivative of secant is secant t tangent t. And so I need this. There's my function. I can cancel out the t, and I'm really left with this part right there. So I'm looking at a of pi over 6. So that's the secant of pi over 6 times the secant of pi over 6 times the tangent of pi over 6. I'm going to move that up to there. So secant of pi over 6, reminder of your unit circle, pi over 6 has a cosine of square root of 3 over 2. So the flip of that is 2 over the square root of 3. Notice I didn't rationalize that, and I don't have to. Square root of 3, and then tangent of pi over 6 means that if the cosine is square root of 3 over 2, that means that the sine is 1/2, so it would be 1/2 over the square root of 3 over 2, which is 1 over the square root of 3. That is a totally numeric answer, and that is totally acceptable. If you wanted to take it the step further and simplify, this is going to be 3, because these two give me 3 with the square root of 3, and 4 square root of 3. Notice, you do not have to rationalize those denominators. You can, but you don't have to. All right. P of t models the size of population t greater than 0. Which of the following differential equations describes linear growth? So all of these are derivatives, rates. Derivative of p, size of the population, the change of population over time. So that's what we're looking at in each of those. So they're asking for which one is the linear graph. This was a multiple choice question on one of the tests. I do remember this one vividly. So what we're looking for is linear growth. Now, if we think about this, if I'm going from p to dp dt, I'm taking the derivative. So the derivative is this number, or is this value. When I take the derivative of a linear function, I get a constant, which is the slope. That's this one. That's the linear one. Okay. The exponential one is back in, I do believe, 8.1, 8.2, 8.3, someplace along there, where we're talking about differential equations and slope fields and separating variables. When you see that, make sure that you're understanding that reminder. If you see the p out here, and that's your independent variable, that is going to be an exponential growth. This one has a p squared. It's not exponential because when you divide it over, you're going to take the antiderivative of 1 over p squared, which you can take. It's not the natural log of anything. This one's going to be the natural log. These two are going to be polynomials. Okay. All right, I'm at the 9-minute mark. I need to get moving here. So determine dz dt. Given that this is the equation, we have a couple of situations here where we have those. So the one thing we don't have is x. So if I know that z is equal to xy squared, and I know that z is 3, and x is x, and y is 1/2, and square it, so that's 1/4 times by 4, so x is 12. All right, dz dt. Notice there's my dz. dz in terms of t. Because there's an x and a y, there is not a t. So anytime I take the derivative, now I'm going to have to use the product rule here. So the first, which is x, times the derivative of the second, which is 2y. But because I am taking the derivative of y in terms of x, or y in terms of t, I need that dy dt because there's no t in here. Plus the second, which is y squared, times the derivative of the first, which is 1 times dx dt. Taking the derivative of x with respect to time. Now, this is just plugging in numbers. So we found x was 12. We found 2 and y was 1/2. We know dy dt is 5. We know y squared is 1/2 squared times the 1 times the dx dt is -2. So we get 60 plus a -1/2, which is 59 and 1/2. Now actually this one is all numeric, so that answer would be acceptable. This answer would be acceptable. Okay. All right, you see a lot of these on here. 4-6. 4-6 is tangent line approximations, finding the equation of the line tangent and then approximating. So given that g of x is a differentiable function, which means it's continuous, g of -3 and 2, that would be that coordinate point, and this is the slope at 3, and that's 7. Use the tangent line. So let's draw or create a tangent line with this. So we got y minus y1 equal to m times x minus x1. So we get y minus 2 is equal to 7 times x plus 3. Now, this is your tangent line equation. Great. Approximate that at -2.9. So y, I'm going to take this 2 over to that side. Y is equal to 7 times x plus 3 plus 2. And notice, don't put or distribute the 7 through. Put in the -2.9 first. And the reason why is, if you notice, this is a little bit easier to do, and it's a little bit easier to multiply by a whole number. Okay, so that is 2.7. Again, if you have any questions, pause this video, slow it down, do anything else. All right, the limit, I just talked about L'Hopital's rule, or if you haven't watched that video, L'Hopital's rule is ahead. If I direct substitute, I get 0 over 0, so that's my indeterminate form. If I look at the limit as x approaches 5 of x squared minus 25, I know that I can factor something out. Okay, so that's one of the ways that we can do the extra thing, do something else. I'm gonna imagine that that's getting factored out, and then what happens is that is left with x squared plus 25. So the limit as x approaches 5 of x squared plus 25 is going to be 5 squared plus 25, which is going to be 50. Now if I did the limit as x approaches 5 of the top and the bottom, L'Hopital's rule would be accepted and used, so I could get 4x cubed over 2x. And if you notice, I can cancel out the 2 and one of the x's, and I get 2x squared. So the limit as x approaches 5 of 2x squared is 2 times 5 squared, which is 50 as well. Okay? So that is the notes for the Unit 4 review. It's about a 15-minute video, it looks like. So once you get done with this, that should help you do the circuit, which I'm going to put up next. I'll do a couple of those problems to get you started on those, and then I will post it on Google Classroom. Have a good night.